Okay, so second half of the infinite graphs teaser. This is a neat little section that will not be further treated in the infinite graphs course, but only here because it's so small, but it is rather neat. So let me do this properly here. And this is about universal graphs. So a graph G let's say a countable graph that has a certain property. That's why this curly p is a p, and the element sign there means it's an element of this class. Just another way of saying it has a certain property. Is universal for P if every graph with this property is contained in this graph G. Now let me call it G star, so this can be an ordinary G. So G star is universal for P if it has this property, itself has this property, and for every graph with this property, this graph is contained in G star. And you see a symbol for contained which doesn't exist in graph theory, or which I haven't introduced. And the reason is that this could be subgraph, it could be induced subgraph, or it could be minor or topological minor, or indeed any other relation for graphs, but those are the four standard ones. Wagner had one slightly weaker, one even weaker than minor, the minor relation, which is rather neat and useful. Nobody's ever thought about it further. So there are four relations that one considers for graphs, and the strongest is induced subgraph, then followed by subgraph, followed by topological minor, and followed by minor. So they get weaker and weaker as we go from left to right. It's easier for a graph to be a minor of another graph than to be a subgraph of another graph. So every subgraph is in particular a minor or a topological minor and so on. Right. So is the notion clear? First we fix one of these relations, call it less than. So for example, minor or subgraph or induced subgraph or whatever. And then we ask, then we fix a property, a graph property, and then we ask, is there a graph with that property that contains all the other graphs with that property? And I always mean countable graphs. They're allowed to be finite, but countable. Okay, so for the ordinary subgraph relation, can you think of a universal graph for P being the class of all countable graphs? So can you think of one countable graph that contains all the other countable graphs as subgraphs? And yes, of course you can. This one here. Right? K aleph naught. The complete graph on countably many, infinitely many vertices is universal for the subgraph relation. It's not universal for the induced subgraph relation, obviously, because as soon as you have a graph that has a non-edge, it's not an induced subgraph of this. Do we have any examples for induced Yes, the infinitely branching tree is universal for the induced subgraph relation for P being all trees. Right? Take a vertex, infinitely many neighbors, each of those has infinitely many neighbors, each of those has infinitely many neighbors. That's this tree, T, Aleph naught regular. And any countable tree is an induced subgraph of that. Now, so how about for all graphs, is there a universal graph with respect to induced subgraphs? That's a good question. Right, so is there a universal graph for induced subgraphs and P all graphs? The answer is yes. So let me show you that. Here's a neat little sufficient condition. So let me, for the next 10 minutes or so, refer to this as simply universal. So the next 10 minutes, universal always means for the property of just being a graph, so for the class of all countable graphs, with respect to the induced subgraph relation. And here's the sufficient condition. If you pick a finite set of vertices, call it U in this graph, and you pick another disjoint finite set of vertices, call it W, then let me make this yellow. Then there exists a vertex that is adjacent to everything in U and not adjacent to anything in W. Okay, it's a harmless looking little property. So once more, for every choice of finitely many vertices, call that set U, and a disjoint set of finitely many vertices, call that set W, there exists a vertex outside those two sets that is adjacent to everything in U and non-adjacent to everything in W. Okay, if G star has this property for all these choices of U and W, then it's clearly universal. Right? Why? Take any old G, a countable graph. Right? That's that looks like a ray, so just countably many vertices. Now let's embed this graph in G star that has this property. That's easy. Suppose we have embedded this much already. Then the next vertex is adjacent to some of these vertices and non-adjacent to some other vertices. Right? So we have embedded these already. So when I say embedded, I mean we have defined an injective map from the vertices here to the vertices of G star that preserves adjacency and non-adjacency. So suppose we've embedded this finite little initial segment of the vertices of our arbitrary G. Then let's look at the next vertex. It has some neighbors in there, and it has some non-neighbors in there. Find their images in our G star. Call the images of the neighbors U. Call the images of the non-neighbors W. They're distinct because that's an embedding. And then there exists something to which we can map this vertex, right? So we've embedded a little more. Okay, so clearly, if a graph G star has this property, then it's universal. Is there a graph with this property? Yes. Even easier. Let's just build it. We start with a vertex, and then we have sort of built a finite graph, and then we add one more vertex in every possible way for choosing finitely many vertices and calling that set U, choosing some finite other set calling that W, and make this vertex, join this vertex correctly to U and W. So when we have built something finite, some finite graph, we can, for every pair of sets U, W, disjoint subsets of the vertices of what we've built, add one correctly joined vertex, a new vertex. There are many choices of U and W in this finite graph, and for every such choice, we add one new vertex. That's our next step. That's another finite graph. And then for that finite graph, we can do the same. Right? So so let's call this property star. Right? Such G exist. Just build it. So for every U and W, we add a new vertex. For a different U and W, we add another vertex. For yet another U and W, we add yet another vertex, and so on. And then repeat. First step, second step, third step. Right. After infinitely many steps, we have constructed a graph with this property, because every finite subset that we might choose in the graph eventually appearing, that finite set will have appeared after some finite time. That's a crucial argument, always the same, not always, often used in infinite graphs. And it will have appeared at some finite time, and the next time we added a tailor-made vertex for this specific choice of U and W. So even the next finite graph already satisfied star for this particular choice of U and W, which was arbitrary in the entire infinite graph. Okay, so it exists. That's cool. So the answer is yes. We've proved that. And now comes a fun part. There's only one graph with this property. What does that mean? It means that any two graphs with this property are isomorphic. Okay? Right. So let me show you that. Suppose let G1 and G2 satisfy star. Let's build a bijection. Let's define a bijection that will be an isomorphism between G1 and G2. So here's G1, here's G2. Enumerate all the vertices. For both graphs. And now define this bijection in infinitely many steps alternating between G1 and G2 in the following way. At odd steps, we look at the first vertex in G1 that hasn't been mapped to anything, and we map it to something. In the second step, we look at the first vertex of G2 that hasn't been mapped to anything. So this has been mapped to something, but this one is even earlier, so that hasn't been mapped to anything. Let's map that to something in G1. But not any old something, because this may or may have an edge sent to here. So we need its image in G1 to mimic this behavior with respect to the partner of that. So we need to map this to a neighbor of this. So for example, to this. Okay, now suppose, this is a bad picture. Suppose we have done this finitely often. Then always pick at odd steps the first vertex that hasn't been mapped to anything in G2 in G1, and at even steps take the first vertex in G2 that hasn't been mapped to anything in G1, and map it so that it is adjacent to the correct vertices, so that its partner, its image, is adjacent to the partners of those of its of the vertices of its own graph that already have partners. Right? So it's a little misleading to draw this as the finite step, because these vertices can be here and there and there and there and there and so on. So we never know. But say, if we want to find a partner for this, we look at its neighbors, we look at the non-neighbors amongst the vertices in its own graph that have partners already upstairs. And for this set of neighbors and non-neighbors, we find the images, which exist by assumption. And then for this, the image of this will be U, the image of this will be W, and when we find a correctly joined vertex up here, and we map this vertex to that vertex. So this could be here. Right? Yes?
Yeah, but why do we know that all those vertices exist in both graphs? Is it because both are infinite?
No. So why do the corresponding vertices in the other graph, why does a corresponding vertex in the other graph exist? Because that other graph by assumption satisfies star. Right? Why are we using up all the vertices? Why is every vertex mapped? Because we're always considering the least one that isn't mapped yet at every step, toggling between G1 and G2 right? Same argument as last time, where we always have to fix an enumeration to make sure that we treat every vertex at least once. Right, so this is the, this is called a back and forth argument. A back and forth argument is a proof technique for universal graphs. All right, more questions? Yeah.
Is there always only one universal graph? Because all
Excellent question. Excellent question. I've shown that there's only one satisfying star. Does that mean there's only one universal graph? Well, it doesn't obviously mean that, because star is only a sufficient condition for being universal. It's not a necessary condition. Is it a necessary condition? Could there be universal graphs that don't satisfy star? Yeah, you can make one very, very easily. Just take one universal graph. Say, take a graph with star. Such things exist. Right, and they're universal. So take one of those. Can you turn it into a graph that's still universal but no longer satisfies star? Just spoil star. Can you spoil that condition by making a little change? Yeah, so, for example, add an isolated vertex. That's a bigger graph, but it's still countable. It certainly no longer satisfies star, because this isolated vertex that you added could be in your set U. And then you won't find a V adjacent to that. And it's still universal, because without that vertex, every countable graph can be found as an induced subgraph of the rest. So, yeah. Yeah, okay, very good question. More questions? Okay, so this graph is called R for Rado, or Rado. Richard Rado was one of the early graph theorists. He emigrated to the UK in the 1930s and became a professor in Reading, where he stayed for the rest of his life. And yeah, so this graph is named after him. In fact, he didn't come up with this property. So he gave an explicit construction of a universal graph that happens to have this property. In the 1960s. This proof, everything here was already known to set theorists in the 1950s. But anyway, so this graph is called the Rado graph. And it's probably the best studied graph of all graphs. There's papers and papers and papers just about this one graph. And the Peterson graph is a close runner-up. There are lots of rather less significant papers only about the Peterson graph. But they're quite exciting things about the Rado graph. So look at the exercises. There's a particularly neat one for set theorists, and most of the exercises I'm not setting it because you're not set theorists, but okay. That's the Rado graph. Right, more properties. We'll be talking about random graphs later in the course, and in a sense, this is the unique countably infinite random graph. One has to define exactly what that means, but once one has done that, one can prove that a countably infinite random graph is isomorphic to this one with probability 1, because that probability is so likely to happen. That property is so likely to happen. So there's essentially only one infinite random graph which has killed random graph theory for infinite graphs, which I can live with. Okay, so that's a nice little aside which we will prove when we get to chapter 11 later. Another observation is group theorists always like transitive graphs. So Cayley graphs, for those of you that have met them, are transitive. A graph is called transitive if for every pair of vertices there's an automorphism of the graph that maps the first of those to the second. So locally, they look the same everywhere. Right? There's an automorphism of the whole graph that maps this vertex to that, so its neighbors here can be found there as well. And so this looks like that. But not just here, but there, and everywhere. So this graph, the Rado graph, is a bit like that. Not a bit, it's very much like that, even in the stronger sense that you can not only map every vertex to every other vertex by an automorphism of the entire graph, but you can take any finite subgraph, no matter how large, 1 million vertices, and find an induced, and for every induced copy of that somewhere else, you can extend this isomorphism to an automorphism of the whole thing. And the proof is very much like that. So those graphs are called homogeneous. So the Rado graph is homogeneous in this sense. The homogeneous graphs, countable graphs, have been classified. You find more about them in the book. The Rado graph is the only interesting one. The homogeneous digraphs are more complicated to classify. And there are two more properties I want to mention. One is that if you make finite changes to the Rado graph, in that you, sorry, a question first? No. In that you delete finitely many vertices, or delete finitely many edges, or add finitely many edges. Or all of these three things at once, but only finitely many changes. That will not kill property star. Well, that's obvious too, right? Suppose you have, I don't know, deleted finitely many vertices or edges. Then you want to show that what remains still satisfies star. Well, you look at the original graph, and those things that you deleted, you just put them in U. And you find a new vertex that is attached correctly to this larger U and W, and in particular to what is left of U and W. And similarly when you add edges. Right. You can't add vertices. Right, as we saw, if you add an isolated vertex, then you're no longer isomorphic to R, and therefore you can't satisfy star anymore. Okay, so finitely many changes, vertex or edge deletions or edge additions don't spoil star. How about deleting half the vertices? By half, I mean delete infinitely many and leave infinitely many. Does the rest still satisfy star? That's an answer? No, clearly not, because you can embed any countable graph in your Rado graph. And do that. That will occupy infinitely many vertices. Delete all the others. Then what remains is not the Rado graph, it's your graph. So for example, a complete graph, an infinite complete graph. You can embed that in the Rado graph. There it is. Delete the rest. The rest is going to be infinite, right? A complete graph, an infinite complete graph plus finitely many vertices will never satisfy star, so the rest must be infinite. Delete this rest, and what remains is complete. It's not the Rado graph. Okay, but something nearly as nice as true. Let me give that a name. Call a graph G, countable infinite graph, indestructible, if for every partition of its vertex set into two sets, one of the two sides is isomorphic to the original graph. So how do I write that? Okay, that was slightly less than elegant. Okay, so G1 is the graph induced by V1, G2 is the graph induced by G2. And the statement is that if you partition G into the vertex set of G into two sides, G1, and take what they induced, then one of these is isomorphic to the entire G. That's the property. Right? Such G are called indestructible. Okay, and the Rado graph is indestructible. Oops. Why is the Rado graph indestructible? Okay. Yeah, so if this is R, could it be that neither half is isomorphic to R? Well, we know what it means to be isomorphic to R. It means satisfying star. Right? Could it be that both halves fail to satisfy star if the whole thing does? Well, no, because if we have a U and W here, well, yeah, okay. Which is bad in that there's no V that is joined correctly to U and W. Suppose this half is not R, does not satisfy star, then this is witnessed by some U and some W. for which there does not exist a V. And similarly here, yeah, but then just consider the union of the two U's. And the union, and call that, so, okay, so this was U1, this was U2, call their union U, and similarly for the W's, then this UW witnesses that the entire graph doesn't satisfy star, because if it did, there would exist a vertex V that is correctly joined to U and correctly not joined to W. But this V would have to live on the left or on the right. And no matter where it lives, it would then witness that U1, W1, or U2, W2 were not counterexamples as we chose them to be. Okay, so that's easy. R is indestructible. Any other examples? Some trivial examples, please. Can you think of a graph, countable graph, no matter how you cut it in two, one of the two sides is isomorphic to the whole thing, yes? Yeah. Right, the complete graph, obviously. You cut it in two. It doesn't even have to be two infinite sides. Just cut it in two. One of the sides is isomorphic to the whole thing. And then, of course, its complement, the graph with countably many vertices and no edges, similarly. Let me prove that these are all theorem, I think theorem, or maybe proposition. Proposition 832. Are the only indestructible graphs. Okay. Okay, let's prove that. Proof. It's such a relief to be unable to say, we apply induction, let's delete a vertex. It's nice to do something constructively. So, right. So proof that G be any indestructible graph. Let's look at a few cases. Case one, G has an isolated vertex. Okay. V naught. Then partition the graph as follows. Take as class 1 all the isolated vertices, and as class 2 the rest. Okay, the rest is not going to be isomorphic to this whole graph because the rest doesn't have an isolated vertex. Careful. If this was an isolated vertex, it wouldn't send any edges to this rest, but it can't send an edge to those vertices either because they are isolated. So they don't send an edge to it. So this would also be isolated in the entire graph, not just in what remains. But if it was isolated in the entire graph, it should be sitting up there. Okay, so this is not G. Therefore, that's G. The set of all isolated vertices spans an isomorphic copy of G, so G is this. Case 2. G has a dominating vertex. That's the opposite of isolated. So a vertex is dominating if it sends edges to all the other vertices. Okay, same proof. Right, class 1 is the set of all dominating vertices. Then the rest cannot be an isomorphic copy of this whole graph because the rest doesn't have a dominating vertex. Not one that dominates it, but also because that will then also dominate the vertices at the top because they are adjacent to it. Right? It's exactly the same proof as here with non-adjacency replaced by adjacency, same thing. And then we get that the graph is complete. Okay, so case 3, there's neither an isolated nor a dominating vertex. Okay, now it gets a little more interesting. Not much, but a little bit. We need to show that the graph is the Rado graph. Okay? If there's neither an isolated vertex nor a dominating vertex, it can't be one of those. So we want to show it's the Rado graph. Suppose G is not the Rado graph. Let U and W witness this. Wit that star fails. Okay, so there's no vertex V correctly joined to U and W, but let's not take any set pair of sets UW that witness the failure of star, but one with as few vertices as possible. So union of U and W minimum. All right, they're finite sets. Let's take a pair UW that is as small as possible. I'm not saying minimal. I'm saying the number of vertices, total number of vertices, is as small as possible. Okay. Then they can't both be empty. Let's ask our expert for the empty graph for a proof. So if U and W are empty, right, then this particular pair of UW does satisfy star, because every vertex is correctly joined to every vertex in the empty set. Okay. If U is not empty, pick an element and do the following. So here's our UW. W may be empty or not, don't care. And here's a little u. Then let V1 consist of U and all the non-neighbors. So V1 is U plus non-neighbors of U. Okay, and V2 is the rest. Then the top cannot be isomorphic to the whole graph because it has an isolated vertex, U. And our graph doesn't have an isolated vertex because we're in case 3. So then G2 is isomorphic to G. And U prime, that is U minus the little u, together with W, do not witness the failure of star in G by the minimality choice of U and W. So, since the rest is isomorphic to G, they don't witness the failure of a star in G2 either. Okay, so there does exist a vertex V that is correctly joined to everything in U prime, which may be empty, and correctly not joined to everything in W, which may be empty. Ha! But this little v is also joined to U, because if it wasn't, it would be sitting up there. That's all the non-neighbors, right? So V does exist for the original U and W, and that's a contradiction to our assumption. Isn't that cool? And of course, the other case, if W is non-empty, is exactly the same, with non-adjacency and adjacency swapped. Yeah, questions? No. Not fun? So we have shown some things about the radar graph, that it's universal, that it's homogeneous, and that it's indestructible. Pretty cool graph, which makes it rather unique as well, unfortunately, or fortunately, as you wish. Yeah, so that's all I want to say about the radar graph. There are some more exercises about it in the book. A final word about universal graphs. So the question, does there exist a universal graph with some particular property, has been considered for other properties. And for a very long time, all the answers were either completely boring or negative. There were some difficult proofs of the non-existence of universal graphs. And for interesting properties such as planar graphs and so on. And the reason they were all negative was basically that the relation they considered was too strong. They considered the subgraph relation or even the induced subgraph relation. That has something to do with the background of the people that did it, who were at least partly set theorists. And by partly, I don't mean that some of them were and the others weren't. All of them were partly, at least, or fully. So for them, yeah, I mean, they have their own view of relations and so on. So the induced subgraph relation was the natural choice for them, and all the results are negative, except for some trivial ones. But for graphs which P are minor universal. Let's take the weakest. Have minor universal graphs in them. And there's a lot more music in that question. So it took us a while to even prove one positive result, but there is one. So there is a minor universal planar graph. And then that was in 1999. Then nothing happened for over 20 years. And then Agalos, Georgakopoulos, proved that there is a minor universal graph in the class of graphs without a K5 minor. There's also one in the class of graphs without a K33 minor. None of these classes has subgraph universal elements and so on. So there are positive results there. And here's a conjecture. Next positive theorem for this question will be by one of you. You go and prove it.